November 1943, Detroit, Michigan. The third shift at the Packard Motor Car Company plant on East Grand Boulevard. The air inside Building 10 smelled of cutting oil and hot metal. Machines screamed. Overhead cranes groaned. And at Station 47, beneath a single work lamp, a woman named Dorothy Marsh held a micrometer against a crankshaft-bearing journal, waiting for the needle to settle. 3/10,000ths of an inch. The tolerance window for a Rolls-Royce Merlin supercharger shaft was narrower than a human hair. Too loose, and the engine would fail at altitude. Too tight, and it wouldn't spin at all. She checked the gauge twice, marked the part and moved it forward. Across the Atlantic, in a concrete bunker at the Rechlin airfield test facility, Luftwaffe engineers were disassembling a captured P-51 Mustang engine. They had examined the metallurgy, analysed the alloy composition, and measured the combustion chamber. Everything matched their own standards. And yet, the Allied engines kept running, flight after flight, mission after mission, with a reliability German factories could not replicate. What baffled them wasn't the design, it was the consistency. They didn't know about Dorothy, or the 10,000 women like her, working in shifts, measuring in shadows, building an air war one tolerance at a time. They were machinists, inspectors, riveters, and line testers. They came from Detroit, Dearborn, and the small Michigan towns along the rail lines. Some had worked in sewing factories before the war. Others had never held a job outside their homes. A few had brothers or husbands already overseas, and most were between 20 and 40 years old. By late 1943, women made up nearly 40% of the Packard workforce on the Merlin program. They weren't there by accident. They were there because the men were gone, and the engines could not wait. The Packard 5-1650. Merlin was not an American design. It was a British one. Rolls-Royce had developed the Merlin in the mid-1930s, a liquid-cooled V12 that powered Spitfires, Hurricanes, Lancasters, and Mosquitoes. It was a masterpiece of engineering. 12 cylinders, a two-stage supercharger, and 1,490 horsepower at peak output, but Britain could not produce enough of them, not with factories under bombardment, not with supply lines stretched thin, and not with the demand climbing every month. In 1940, Rolls-Royce licensed the design to Packard. The deal was signed in September. Production began in 1941, and by 1943, Packard was building more Merlins than Rolls-Royce itself. The engines went into North American P-51 Mustangs, the long-range escort fighters that would turn the air war over Germany. They went into Canadian-built Lancasters, and they went into any airframe the Allies could mount them on. The demand was relentless. But the Merlin was not an easy engine to build. It had over 14,000 individual parts, and the tolerances were measured in 10,000ths of an inch. The crankshaft alone required 35 separate machining operations. The supercharger impeller had to be balanced to within a fraction of an ounce, and a single miscalibrated drill bit could ruin a cylinder block worth hundreds of man-hours. Every engine had to perform identically. A pilot climbing to 30,000 feet over the North Sea could not afford an engine that ran 5% weaker than specification. 5% meant falling behind the formation. It meant becoming a target. And it meant not coming home. The Packard plant on East Grand Boulevard ran 3 shifts, 24 hours a day and 7 days a week. At peak production in 1944, the facility employed over 36,000 workers. The Merlin lines occupied multiple buildings, building 10 handled crankshafts and connecting rods, building 12 assembled cylinder blocks, and building 15 was final assembly and testing. The noise was constant. Lathes, grinders, milling machines, and drop hammers. The floor vibrated, and the air tasted metallic. Dorothy Marsh worked in the gauge room in Building 10. Her job was to verify that every crankshaft met tolerance before it moved to the next station. She used micrometers, calipers, and fixed gauges. She checked journals, throws, and bearing surfaces. And if a part was out of spec, she marked it with a red crayon and sent it back for rework or scrap. She worked standing up for 8 hours. Her hands were stained with layout dye, and her fingertips were calloused from handling metal. Across the plant, Helen Kowalski ran a horizontal boring mill, cutting cylinder bores to exact diameter. Margaret Hayes operated a crankshaft grinder, chasing tolerances under a jeweler's loupe. And Ruth Simmons worked final inspection, checking torque values on connecting rod bolts with a calibrated wrench. There were thousands of them, each one responsible for a specific operation, and each one knowing that a mistake would not show up until an engine failed at 25,000 feet. The broader war context pressed down on every shift. By November 1943, the 8th Air Force was losing bombers faster than they could be replaced. Unescorted, B-17 and B-24s were being mauled over Germany, and the losses ran as high as 20% on some missions. The P-51 Mustang, powered by the Packard Merlin, was the answer. But only if the engines kept coming, only if they worked, and only if every single one could be trusted. Every error was a pilot's life, and they knew it. The problems started showing up in the first 6 months of full production. Parts that passed initial inspection were failing final tests. Crankshaft journals measured correctly in the gauge room but were rejected at assembly. Cylinder bores held tolerance on the first shift but drifted by the third, and connecting rod bolts torqued to specification on Monday were loose by Friday. The issue wasn't the workers, it was the system, or rather, the lack of one. Each station operated independently. Inspectors used their own gauges. Machinists set their own tooling, and supervisors managed their sections without coordinating methods across shifts. What worked in Building 10 didn't transfer to Building 12. A technique that reduced scrap on the day shift was ignored at night, and nobody tracked why identical operations produced different results depending on who was working. The rejection rate climbed. In early 1943, roughly 12% of machined parts failed to meet tolerance and had to be scrapped or reworked. That meant 1 out of every 8 crankshafts, 1 out of every 8 cylinder blocks. Hours of machine time wasted, tons of aluminum and steel sent back to the scrap pile, and engines delayed while replacement parts were produced. The supervisors noticed, and they responded the way supervisors always did. They told the workers to be more careful. They posted reminders about tolerances. They held meetings about quality, but they didn't change the process, and the scrap kept piling up. Some of the male engineers doubted the women could handle the precision required. The sentiment was rarely spoken aloud, but it hung in the air during shift changes and production meetings. A few supervisors suggested rotating the women to less critical tasks. Others recommended bringing in more experienced machinists from other plants, and a handful quietly questioned whether women belonged in precision work at all. Dorothy Marsh heard the whispers. So did Helen Kowalski, and Margaret Hayes, and Ruth Simmons. They said nothing. They kept measuring, they kept checking, and they kept sending parts forward that met every specification on paper, but somehow still failed downstream. The real problem was invisible to management. It was the gauges themselves. Micrometers and calipers were calibrated at the start of each week, but they drifted during use. Metal contact wore down anvil faces, springs weakened, and temperature changes in the plant altered readings by fractions of 1/1000th of an inch. A gauge reading 0 on Monday morning might read +0.02 by Wednesday afternoon, and nobody was rechecking them between calibrations. Then there were the fixtures. The jigs and clamps that held parts during machining were supposed to be identical across all stations, but they weren't. Some were worn, some were shimmed differently, and some had been modified by individual machinists who thought they knew better. The result was that identical parts were being machined to slightly different reference points, and those tiny variations accumulated as parts moved down the line. The pace made everything worse. Packard was under contract to deliver 400 engines per month by mid-1943. That number would climb to 500, then 600. Every delay rippled forward. A rejected crankshaft meant waiting 3 days for a replacement. A failed cylinder block pushed an entire engine back 2 weeks. And the pressure came from the top down. Military liaison officers visited the plant weekly. They asked questions. They reviewed production logs. And they reminded everyone that pilots were dying because there weren't enough Mustangs over Germany. The women on the line felt it more than anyone. They adjusted their techniques, but scrap piled. They double-checked measurements, but tolerances slipped. And they recalibrated their gauges, but drift continued. The harder they worked, the more the system resisted them. By summer 1943, the rejection rate had climbed to 15%. Packard was falling behind schedule. Military inspectors were threatening to pull contracts, and plant management was running out of explanations. Something had to change. Not the workers, not the machines, but the method itself. Engines couldn't wait for perfection, but perfection had to speed up. The shift happened quietly, not in a management meeting, not in an engineering office, but on the floor during the second shift in Building 10, where the gauge room workers gathered during their 15-minute break. Dorothy Marsh set her coffee down on a workbench and pulled out a small notebook. She had been tracking her own measurements for 3 weeks. Crankshaft journals, bearing surfaces, tolerance drift, and she had noticed a pattern. Parts she checked early in her shift almost always passed final inspection. Parts she checked late in her shift were rejected at twice the rate. The parts hadn't changed, but something else had. Helen Kowalski leaned over to look at the numbers. She worked the boring mill 2 stations down, and she had been keeping notes too. Her cylinder bores were drifting the same way, tight in the morning, loose by afternoon, and the pattern repeated across every shift. "It's the gauges," Dorothy said. "They're walking." Margaret Hayes nodded. She had suspected it for weeks but hadn't been able to prove it. The micrometers were calibrated once a week, but nobody checked them between calibrations. And metal tools expanded and contracted with temperature. The plant was hot. The machines were hot. And the gauges spent 8 hours in contact with warm metal parts and warmer hands. Ruth Simmons added another piece. The fixtures were inconsistent. She'd noticed it during final assembly. Connecting rods torqued to the same specification behaved differently depending on which jig they came from. Some jigs were worn, others were shimmed, and a few had been modified by machinists who thought they were improving the setup. The result was a system with dozens of small variables that nobody was controlling. The solution wasn't a single idea. It was a series of small ones, and they came from the workers who lived with the problems every day. First, the gauges. If they drifted during a shift, then check them more often. Dorothy proposed a mid-shift calibration. Every 4 hours, gauges would be verified against a master set kept in a temperature-controlled cabinet. It would take 10 minutes per shift, but it would catch drift before bad parts moved downstream. Second, the fixtures. If jigs were inconsistent, then standardize them. Helen suggested color-coding shims by thickness and documenting every fixture setup. Red shims for 0.5 thousandths, blue for 1 thousandth, yellow for 2. And each jig would have a setup card showing exactly how it was configured. No modifications without approval, no guessing, and no improvisation. Third, the workflow. If techniques varied between workers, then share what worked. Margaret proposed a daily logbook at each station. Workers would record any issues, any adjustments, and any tricks that improved results. The next shift would read the log before starting, and supervisors would review the logs weekly to identify patterns. Fourth, the training. If precision was critical, then teach it properly. Ruth suggested pairing new workers with experienced ones for the first 2 weeks, not just shadowing, but hands-on work with supervision. And each new worker would have a checklist of skills to master before working independently. None of these ideas were revolutionary. They were just systematic, and they were exactly what the process needed. Dorothy brought the proposal to her shift supervisor, a man named Frank Hutchins. He was skeptical at first. Mid-shift calibrations would slow production. Color-coded shims seemed unnecessary, and logbooks created paperwork. But Dorothy had numbers. She showed him the rejection rates. She showed him the correlation between gauge drift and scrap, and she showed him how much time was being wasted on rework. Hutchins agreed to a trial. 1 week, 1 section, building 10, second shift. If it worked, they would expand it, and if it didn't, they would drop it and go back to the old way. The trial started on a Monday in late August 1943. Dorothy and 5 other women implemented the new system on the crankshaft line. Mid-shift gauge checks, standardized fixtures, documented setups, and shared notes. By Friday, the rejection rate on their line had dropped from 15% to 4%. Scrap was down, rework was down, and output was up because fewer parts had to be redone. If perfection was too slow, maybe precision could move faster. Not through magic, but through method. The system spread faster than anyone expected. By the end of September, all 3 shifts in Building 10 were using the new methods, and by October, Buildings 12 and 15 had adopted them too. The mid-shift gauge checks became routine. Every 4 hours, workers would pull their micrometers, calipers, and fixed gauges from their toolboxes and verify them against the master set in the temperature-controlled cabinet. If a gauge had drifted more than 0.5 it was pulled from service and recalibrated. And if it drifted consistently, it was replaced. The 10-minute check became as normal as clocking in, and nobody questioned it after the first week. The color-coded shim system transformed the fixture problem. Red shims sat in labelled bins next to blue ones and yellow ones. Each machining station had a setup card clipped to the fixture frame, showing exactly which shims were installed and where. And when a worker started a shift, the first thing they did was verify the fixture matched the card. No improvisation, no guessing, just set up, check and run. The logbooks became the central nervous system of the operation. Each station had a simple ruled notebook kept in a metal clip on the machine. Workers recorded the date, the shift, their name, and any observations. Fixture C vibrating at high speed, tightened mount bolts. Tool 14 cutting oversize, replaced. Parts running cold, increased preheat time. And the next shift would read the last entry before starting work. Problems were documented, solutions were shared, and patterns emerged that would have stayed invisible without the logs. Training slowed initial output, but improved everything downstream. New workers spent their first 2 weeks paired with experienced machinists or inspectors. They learned how to hold a micrometer without warming it with body heat. They learned how to feel when a cutting tool was wearing. And they learned how to read the metal, to see when a bore was starting to chatter or when a grind was loading up with swarf. The checklist ensured nobody moved to independent work until they could perform every operation to standard, and the reject rate among new hires dropped from 22% to under 7% within 3 months. The rhythm of the line changed. Workers measured, they marked, and they moved on. There was a cadence to it now, a predictability that hadn't existed before. Dorothy would check a crankshaft journal, compare it to the spec card, mark it with a green wax pencil if it passed, and slide it forward on the roller track. 8 seconds per part, 40 parts per hour, 320 parts per shift, and each one within tolerance. Helen ran her boring mill with the same discipline. Set up, verify, cut, measure, log. Her cycle time dropped by 12% because she wasn't stopping to troubleshoot mystery problems, and her scrap rate fell to 2% because she caught tool wear before it pushed parts out of spec. Margaret and Ruth worked with the same steady precision. No wasted motion, no guessing. Just the method, repeated 1,000 times per shift until it became instinct. And the parts kept moving forward, clean and true and ready for assembly. The rejection rate across the Merlin program dropped from 15% in July to 6% in October to under 4% by December. Scrap tonnage fell by 2/3, rework hours dropped by half, and engine output climbed from 380 units per month in August to 487 in November. Packard was not only meeting its contract targets but exceeding them. The supervisors noticed, the engineers noticed, and the military inspectors noticed. What had been a struggling program was now a model of precision manufacturing. The women who had been doubted 6 months earlier were now being studied. Other departments sent observers to watch the process, and other plants began adopting the same methods. Across the ocean, German engineers would soon see the results, not in a factory, but in the sky, where the engines they couldn't understand were already turning the air war in favour of the Allies. By early 1944, the Packard Merlin was performing beyond specification. Flight test data from Wright Field in Ohio showed consistent power output across production batches, and engine failure rates in operational squadrons had dropped to less than 2%. Pilots were reporting smooth operation at altitude, reliable starts in cold weather, and predictable performance under combat stress. The engine had become something rare in wartime production, trustworthy. The P-51 Mustang, powered by the Packard Merlin, began arriving in Europe in large numbers by spring 1944. Long-range escort missions over Germany became routine, and bomber losses dropped dramatically. Formations that had suffered 15 to 20% attrition were now losing 3 to 5%. The difference was measurable in lives, in aircraft, and in mission success rates, and the difference started in a factory in Detroit where women measured crankshafts under work lamps. The German response was confusion. Luftwaffe. Intelligence units began collecting data on captured Allied aircraft and engines. Technical officers at Rechlin, the primary Luftwaffe test facility, conducted detailed examinations of recovered Merlin engines. They disassembled them completely and measured every component. They analysed the metallurgy, tested the alloys, and compared the specifications to German standards. And they found nothing unusual. The materials were good but not exceptional. The design was sound but not revolutionary. The tolerances were tight but achievable. What baffled them was the consistency. Every engine performed identically. Power curves matched across serial numbers, separated by thousands of units. Compression ratios held. Bearing clearances stayed within specification, and operational reliability remained high even after hundreds of flight hours. German factories could not replicate that level of uniformity. BMW, Daimler-Benz, and Junkers all produced excellent engines, but batch-to-batch variation was inevitable. Some engines ran strong, others ran weak. and field mechanics spent considerable time adjusting and compensating for manufacturing inconsistencies. A captured technical report from late 1944, recovered after the war, included notes from a Rechlin engineer examining a Packard Merlin serial number Vi-1650-7432. The report noted exceptional machining precision and uniform surface finish on all rotating components. It questioned how such consistency could be maintained at production scale, and it recommended immediate investigation into Allied manufacturing methods. The engineer noted that German production emphasized individual craftsmanship, with skilled workers adjusting each engine to compensate for part variations. The Allied approach appeared to eliminate variation at the source, and the result was faster assembly, fewer field adjustments, and higher reliability. Japanese technical teams reached similar conclusions. Captured Merlin engines in the Pacific Theater were shipped to Mitsubishi and Kawasaki facilities for study. Engineers marveled at the uniformity of parts and the minimal hand-fitting required during assembly. Japanese production methods, like German ones, relied heavily on skilled final assembly workers who individually adjusted clearances and fits. The Packard engines required almost no adjustment. Parts fit correctly the first time, and torque specifications were consistent across all fasteners. The true shock was not power output, it was repeatability, not miracle metallurgy, but measured work, done 1,000 times correctly. The Liberty women had turned precision into a system, and the system had become a strategic advantage. By war's end, Packard had produced 55,523 Merlin engines. The rejection rate never rose above 5% after late 1943. Final assembly time per engine dropped from 175 hours to 97 hours. And the cumulative man-hours saved exceeded 4 million across the program. Those hours translated directly into additional engines, faster delivery schedules, and more aircraft in the fight. The methods developed on the Packard Merlin lines spread to other programs. Boeing adopted similar gauge check protocols for B-29 production. Chrysler used color-coded fixture systems in tank engine assembly, and Ford implemented shift logbooks across its Willow Run bomber plant. The improvements were documented, studied, and replicated, and the culture of precision measurement became standard practice in American wartime manufacturing. The women who built the system rarely received recognition by name, but their work spoke in engine hours, in missions flown, and in pilots who came home. Not through legend, but through process. Not through individual genius, but through collective discipline. They had built more than engines. They had built a standard. The methods didn't end with the war. They became permanent features of American manufacturing, and they shaped the post-war industrial landscape in ways that would take decades to fully appreciate. Packard continued Merlin production until 1950, producing engines for military and civilian applications long after VE Day and VJ Day. The gauge check protocols, color-coded fixture systems, and shift logbooks remained standard practice, and new workers were trained in the same methods Dorothy Marsh and Helen Kowalski had developed during the desperate years of 1943 and 1944. The culture of precision had taken root, and it outlasted the crisis that created it. Other industries adopted similar approaches. Aircraft manufacturers standardized their inspection procedures and implemented mid-shift calibration checks. Automotive plants began using color-coded tooling and documented fixture setups, and heavy equipment manufacturers introduced shift logbooks to track machine performance and operator observations. The principles were simple enough to travel across industries, and the results were consistent: lower rejection rates, faster throughput, and higher product quality. Some of the women stayed in manufacturing after the war. Not all, but more than the popular narrative suggests. Dorothy Marsh continued working at Packard until 1952, eventually becoming a quality control supervisor overseeing gauge room operations across multiple buildings. Helen Kowalski transitioned to tool and die work, and she spent 30 years as a precision machinist before retiring in 1974. Margaret Hayes left the factory in 1946, but returned in 1951 when her husband's machine shop needed an inspector. And Ruth Simmons became a technical trainer, teaching new hires the same methods she had helped develop during the war. Their contributions were rarely acknowledged publicly. There were no medals, no commendations, and no monuments. The official histories of the Merlin program focused on engineers, contracts, and production statistics. The women appeared, if at all, as anonymous line workers in photographs or as footnotes in labour reports. And for decades, their role in creating the systems that made mass precision possible remained invisible outside the factories where they worked. The broader legacy was structural. American manufacturing in the 1950s and 1960s was built on the foundation of wartime process improvements. The discipline of documented procedures, standardized tooling, and continuous measurement became embedded in industrial practice, and companies that adopted these methods outperformed those that relied on individual skill without systematic support. Quality control evolved from final inspection to in-process verification. Training shifted from apprenticeship observation to structured skill development, and the idea that precision could be systematized, that it didn't require individual genius but collective method, became the baseline assumption of modern manufacturing. By the 1980s, when American industry faced new competitive pressures, some of these lessons had been forgotten. The emphasis shifted back to automation and individual heroics, and the unglamorous work of process discipline was often overlooked, but the principles remained sound. Measure consistently, document procedures, standardized tooling, train deliberately, and build systems that make precision repeatable. These were not secrets. They were methods proven under the most demanding conditions imaginable. The Liberty Women didn't invent precision manufacturing. They refined it under pressure, and they demonstrated that ordinary people, given clear standards and systematic support, could achieve extraordinary consistency. The gauges they calibrated were ordinary. The fixtures they color-coded were standard equipment, and the logbooks they maintained were simple ruled notebooks. But the discipline they applied to these ordinary tools created results that enemy engineers could not explain. Not myths, but measurements. Not miracles, but mastery. Not legends, but method applied 1,000 times correctly. The Liberty Women didn't build folklore, and they didn't chase recognition. They built engines. And in doing so, they built a standard of precision that helped win a war and shaped an industry. The true victory was not in the engines themselves, but in the proof that process could triumph over chaos, that discipline could defeat improvisation, and that ordinary hands, guided by systematic method, could produce work that looked like magic to those who only saw the result. The women of Packard didn't need to understand every principle of aerodynamics or thermodynamics. They needed to measure correctly, document honestly, and move forward with confidence. And they did exactly that, shift after shift, part after part, until the war was won.